parler pour voir. Welcome everyone. Today I will talk about the work I did during my PhD under the title on galaxy cluster modeling in the context of cosmological analysis. Before diving into the details, okay. Yeah. clusters is the gravitational collapse. That happens when a density perturbation is above a certain critical threshold. At that point, the gravity in the overdense region starts dominating. The region decouples from the expansion of the universe and starts collapsing, forming a gravitationally bound realized object. Galaxy clusters are formed from the collapse of the highest density peaks in the initial perturbation field, which are located at the nodes of the cosmic web connected to cosmic filaments. They are therefore the most massive gravitationally bound objects that we can find in the universe today, with masses ranging between about 10 to the 14 to over 10 to the 15 solar masses. Clusters are multi-component objects formed mostly of dark matter, which composes about 80% of the matter content and dominates the gravitational potential. The second most important component is the gas, which is in a hot and ionized state, temperatures ranging between 10 to the 7 and 10 to the 8 Kelvin, and makes up about 15% of the mass of clusters. Finally, we have galaxies that, despite giving their name to galaxy clusters, only form about 5% of their mass content. Being multi-component objects, they are also observable at different wavelengths. Starting from the right, we have the galaxies can be observed through their starlight optical and infrared, near-infrared wavelengths. The gas emits via thermal Bremsstrahlung in X-rays and can be also observed through the inverse Compton scattering of cosmic microwave background photons, a process that is known as Strunia-Zadovich effect at sub-millimeter wavelengths. Finally, the dark matter can be indirectly observed through its gravitational lensing effects on background sources. Galaxy clusters, being the endpoint of structure formation, encode information about the cosmological model. As we can see from this picture, where 4 different universes are simulated starting from different values of cosmological parameters, in particular omega m, that corresponds to the matter density of the universe, sigma 8, the amplitude of matter fluctuations, and W, that identifies the energy of dark energy equation of state. As we can see from the image, the number and distribution of the highest peaks associated with clusters change drastically with changing cosmology. Therefore, we can extract cosmological information from galaxy clusters in many different ways. For example, we can study their distribution through their clustering, or similarly with the Strunia-Zadovich power spectrum, of which clusters form an important part of the signal, or use them as geometrical probes, comparing the X-ray observations with the SZ observations, or as single objects, studying their gas fraction or their matter profile. Another way, which is the one I will be focusing on for the rest of my talk, is galaxy cluster number counts, which are the number of clusters as a function of mass and redshift. Doing cosmology with cluster number counts essentially amounts to comparing the number of clusters observed from in the sky with the number predicted from theory. Matching the model with the observational data, we can put constraints on the cosmological parameters. This has been done by many different with many different observations, finding consistent and competitive results compared to other probes. Nonetheless, there seems to be a rather average preference for cluster data for lower values of omega m and sigma 8 compared to CMB observations. This fact, combined with the upcoming and future surveys, which promise to provide an order of magnitude larger number of the samples of clusters compared to what we have today, motivates us to study all the possible sources of biases in the predicted number of clusters. In order to predict cluster counts that are comparable with observations, we need 3 main ingredients. The first one, the Elo mass function, encodes the dependence on the cosmology and the theory of structure formation, and predicts the number of dark matter halos as a function of mass and redshift. But we cannot observe clusters mass directly,
So we need some scaling relations that relate the mass with the cluster observables that you can see in the sky. Finally, we need a selection function that encodes information about the survey and the detection strategy. All these ingredients rely on some simplifying assumptions, and in particular, all three depend directly or indirectly on the model of galaxy clusters. In most cosmological contexts, the galaxy clusters model is based on three main simplifying assumptions. The first one is the clusters are spherically symmetric, isolated objects, and they are in hydrostatic equilibrium. This gives rise to the so-called self-similar model introduced by Kaiser in 1996 that states roughly that all clusters look the same, or rather that they are scaled version of each other. As a consequence, clusters share universal profiles for the thermodynamic quantities, and the scaling relations can be computed analytically. But we know that in reality, clusters are more complicated than that. We see from observations and simulations that they are not generally spherically symmetric, and we know that living in the cosmic web, they are not isolated and they are connected to cosmic filaments. Therefore, in order to do precision cosmology, we need to model accurately the clusters and their population. Among the many things that can impact the cluster model, we can have, for example, evolution of thermodynamic profiles, departure from spherical symmetry, or connected filaments. And in turn, the cluster model has an impact on many aspects of cosmological pipeline, as we said, the halo mass function, but also the cluster detection, the sample characterization, and the scaling relations. These are interesting aspects to study in my work. I focus mostly on these three particular aspects. On the side of the things that impact the model, I focused on the departure from spherical symmetry and the connected filaments, while on the effect of the model, I focused on the selection function. These are the topics of the rest of my talk, which are presented here and be divided in two parts. First, I will talk about galaxy clusters beyond spherical symmetry, presenting two studies I did studying statistically and in a single object, the distribution of matter in and around clusters. Then I will talk about cluster detection and selection function, presenting a work I did on the completeness function of Planck clusters. So, going with part two, we start from the question, how justified is spherical symmetry? So we see in this video from the illustrious TNG simulation the formation of a galaxy cluster seen through its gas content. The first thing that we can notice is that matter accretes into the cluster not in an isotropic way, but rather through filaments. And also that different clusters and groups tend to merge with each other, giving rise to dynamically disturbed systems that are also disturb the morphology of the cluster. Therefore, we can conclude that we expect galaxy clusters in general to be not spherical. Furthermore, in cluster outskirts, when filaments connect to the clusters, we have a whole lot of physics of accretion that takes place at the interface between filaments and clusters. Therefore, studying these regions can be particularly interesting to understand these processes that are crucial for the interpretation of cluster observations. So, therefore, it is important to quantify the departure from spherical symmetry, understand the physical processes that produces and the implications that it can have on the cosmological pipeline. Therefore, the goal of the second part will be to probe the shape of the matter distribution in and around galaxy clusters, focusing in particular on the gas, that is the main baryonic component. So, I will start by presenting a work I did under the title Gas Distribution from Clusters to Filaments in Illustrious TNG. This is a statistical analysis of the matter distribution in and around simulated galaxy clusters, where we want to compare the 2D matter distribution of clusters with some cluster properties, both structural and physical. We used simulated clusters from the Illustrious TNG, that is a cosmological hydrodynamical simulation with a 300 megaparsec white box from which we take the snapshot at redshift 0. We select clusters by their mass, and we extract both dark matter and gas within 5 times the cluster radius. Then we project these 2 components along 3 directions, obtaining 1,245 cluster images that are the basis of our analysis. We decided to use 2-dimensional projected cluster distribution in order to be more comparable with observations. In order to study the matter distribution in clusters, among the many different options, we decided to use the aperture multipole decomposition that allows us to probe different shapes, azimuthal shapes of the matter distribution in an homogeneous framework. Each multiple is associated, as is shown in this picture, with a particular azimuthal symmetry. Another important aspect of this method is the choice of the aperture, that is the area within which we perform the analysis and the composition. In this work, I took 2 different apertures, one inside clusters and one outside, from 1 to R200. Finally, in order to compare the results between different clusters, we need a normalization, and therefore we divide the power of the multiples by the power of the order 0 that represents the circular symmetry. We call these the multipolar ratios, and we identify by the symbol beta m. These are computed for all the clusters for dark matter and gas particles in both apertures, that is, within and without, inside and outside clusters. So, presenting the results now, we started by investigating the relation between some of the multiple orders with structural properties of clusters, computed from their 3-dimensional matter distribution. The first one that we tested is the center offset. That is the distance between the peak of the distribution and of the matter distribution and the center of mass of the distribution, identified here in orange in the picture, normalized by the cluster radius. We related this with the order 1 multiple that tests the asymmetry of the 2D field with respect to a given axis. And we see from this figure that the 2 are indeed directly correlated with clusters that have a smaller miscentering, having smaller also asymmetry in the distribution, and the contrary, obviously, for large values. Therefore, we can conclude that the multiple 1 is related to the miscentering of the mass distribution. Second, we tested the ellipticity of the dark matter and gas distribution. And we related this to the order 2 multiples, that is, tests the distribution of an elongated shape along a certain axis. Again, we see a very good correlation between these two parameters, proving that the multiple 2 is a tracer of the elliptical shape of the mass distribution. Going further, we wanted to test also the ability of the overall level of asymmetry of the clusters, that is, the departure from spherical symmetry, with respect to some non-observable physical properties. We probed the level of asymmetry with the beta parameter, which is the sum of the first 4 beta m orders, which are the most important in the decomposition. The beta goes from 0 for a spherical object to higher values for less spherical. So we tested 3 different physical properties. The first one is the relaxedness, that probes the level of dynamical disturbance of clusters. Smaller values are associated with more disturbed clusters, and as we see in this figure, those are also associated with less spherical matter distributions. On the other side, more relaxed clusters also tend to be more spherical. The second property that we tested is the accretion rate. That is the rate at which matter falls into the cluster. And as we see, there is a direct correlation in this case with the level of asymmetry, with slower accreting clusters being generally more spherical, while faster accreting ones being more disturbed or less spherical. Finally, we related the level of asymmetry with the formation redshift. That is the redshift at which the mass of the cluster was half of what it is at redshift 0. And again, we see an anti-correlation between the level of asymmetry and the formation redshift. With more recently formed clusters being less spherical and earlier formed clusters being more spherical. Therefore, we can conclude that azimuthal asymmetry generally of cluster mass can trace its dynamical state, and it's also affected by the assembly history of clusters. Finally, going to the cluster outskirts, we wanted to test how the asymmetry of the matter distribution in the outskirts relates to the number of cosmic filaments connected to the cluster. And we define the connectivity as the number of filaments crossing a surface of 1.5 times R200. We see from the figure here that there is a direct correlation between the asymmetry level and the connectivity, with more connected clusters again being less spherical than less connected one. Therefore, the asymmetry in cluster outskirts is related to the filamentary structures that are connected to clusters. So as a summary, we see that inside clusters, some azimuthal features can be used as tracers of the cluster shape and structural properties, and in general, the matter asymmetry can be related to the cluster dynamical state and assembly history, while in cluster outskirts, the large-scale filamentary structures of the cosmic web can impact both dark matter and gas distribution in cluster outskirts. Building on this last result, we wanted to test if indeed the gas in cluster outskirts can be used as a tracer of these cosmic web filaments. Therefore, we decided to probe the distribution of gas in the outskirts of a particular cluster. So first, gas in filaments is notoriously very difficult to detect, mostly due to its low density and low temperature. So far, this has only been done via stacking, for example, by Tanimura et al., or in some very special cases. One of these special cases are the outskirts of A2744, which is a nearby massive disturbed cluster, which was observed in 2015 by Eckert et al. In X-rays, and the authors identified visually the X-ray emission from large-scale filamentary structures. So the goal of my work was to revisit this data on A2744 and try to detect filaments using automatic statistical methods. As data, we used the same observations as Eckert et al. In 2015 and spectroscopic galaxies catalog compiled by Owers et al. In 2011. And on the method side, we decided to use two different methods. One, we used again the aperture multiple decomposition to trace the azimuthal symmetries in the data, and the T-Rex filament finder, which is designed to trace filamentary structures in discrete data sets. Talking briefly about the data that we use, this is an observation in X-rays done by XMM Newton for 110 kiloseconds, which has been reanalyzed using the XCOP pipeline, from which we extracted a surface brightness map of the soft X-ray energy band, which we corrected for the exposure and filtered the point sources. On the galaxy side, as I said, we use a spectroscopic galaxy catalog compiled by Overs et al., of which we performed a selection in redshift and magnitude, and we perform also a correction of the finger of God effect, obtaining a total of 305 galaxies that are shown in the picture as red dots overlaid to the X-ray data for visualization. Starting from the first method that we used, again the aperture multiple decomposition, due to the different nature of the two data sets, we decided to use separate approaches for the aperture of the analysis. In X-rays, we decided to use two apertures, one inside and one outside the video radius of the cluster, while the low statistics of the galaxy data led us to choose a larger aperture that takes into account all the galaxies in the data sets that are further away than 0.6 times the video radius. In order then to identify also the spatial location of the structures identified with the multiples, we performed a map reconstruction of the multiples, obtained resumming the contribution from the multiples, excluding the large, the high order, which are not associated with large-scale filamentary structures. And this is the result that we obtain for the X-ray data with the multiple analysis. On the left, we have the multiple decomposition for the two apertures that we used, in green and in orange. In green, the inner, and in orange, the outer one. We see, starting from the inner aperture, that the multiple decomposition is dominated by two multiple orders, the order 1 and the order 3. And indeed, we see from the reconstructed map that a combination of these two leads to the detection of two main structures that are one in the south and one roughly in the northwest of the cluster. Going to the outer aperture instead, we see that the multiple decomposition is instead dominated only by the order 3, associated with three structures. And indeed, in the reconstructed map, we can clearly identify three structures, again in the south, in the northwest, and in the east. We notice also the good spatial agreement between the inner and the outer aperture for the south and the northwest structures. Going to the analysis of the galaxy data instead, due to, again, to the low statistics, we see that the multiple decomposition is noisier. Nonetheless, we can identify two multiple orders that at low orders that dominate the distribution, which are this time the order 2 and the order 3. This leads of a reconstructed map where two structures are easily identified in the northwest and in the east of the cluster. Going to the second method that we used, the T-Rex filament finder, where T-Rex stands for tree-based ridge extractor. That is a method that is designed to extract filaments in discrete data using a tree topology that is optimized on the data to trace the ridge of the filamentary distribution. This procedure is repeated in several times in a bootstrap approach to obtain a probability map of the position of the filaments. We applied this method to the X-ray data, and we find this result as a probability map. From here, we can trace 4 main large-scale structures extending from the filaments. One in the south, one in the northwest, one in the east, and one in the north. Then, applying T-Rex on the galaxy distribution, we wanted to see if indeed we can retrace the same filaments. And one advantage of the use of spectroscopic galaxies is that we can access the whole 3-dimensional distribution, which we can also probe with T-Rex. Here we show the 3-dimensional box with the galaxies and the identified filaments, and we show here on the bottom the 3 projections. Start from the line of sight projection, and we see that there are again 3 filamentary structures that extend from the center of the cluster, again in the south, in the northwest, and in the east. Interestingly, we see also that from the other 2 projections along the line of sight, which is horizontal in both pictures, elongated structures that extends both in the front and in the back of the cluster that can be associated with filamentary structures connected to the cluster along the line of sight. We also see a somewhat disconnected structure in the back of the cluster, also extending in the line of sight, corresponding roughly to a peak in the south of the center of the cluster. Comparing the results of the 2 methods on the X-ray data, we see a very good spatial agreement between the multiples and the T-Rex identified structures for the northwest, south, and east structures. And instead, we see no counterpart in multiple data for the T-Rex identified northern structure. On the other hand, for the galaxy data, again we see a good spatial agreement for the structures in the east and in southwest, and we see a slight hint for a southern structure, but there is rather low galaxy signal in this region, which is possibly due to selection effects of the spectroscopic catalog, as detailed already by Owers et al. In 2011. Then, comparing the 2 different data sets between the 2, we see that the east and the northwest structures are confirmed by all probes and methods, and while we have multiple confirmation for the southern structure. These are also in very good overlap with the regions identified as bona fide filamentary structures in Eckert et al. 2015, shown here by the ellipses. So, in summary, we report the first blind detection of gaseous filaments in the outskirts of A2744, from which we identified 3 large-scale filamentary structures from the X-ray analysis alone, and their location matches relatively well with the structures identified from the galaxy distribution. This tells us that those are indeed the connection to the cluster of large-scale cosmic filaments. And furthermore, from the 3D galaxy distribution, we also detect 2 other filamentary structures along the line of sight, extending in the front and in the back of the cluster. So this was the end of part 2, and for part 3, I will talk about instead the impact of the cluster model on the detection of clusters and the selection function. In particular, focusing on the completeness function of Planck clusters. Sorry. So galaxy clusters are detected in Planck data using the different the maps at different frequencies through the Sunyaev-Zeldovich effect, which is distortion, a spectral distortion of the cosmic microwave background in the position of galaxy clusters due to inverse Compton scattering. Combining the information on the spectral shape, which has a characteristic shape related to the Sunyaev-Zeldovich effect, with a spatial template for the cluster emission in the matched multi-filter method, galaxy clusters can be identified, and the method returns a catalog of detections containing position, estimated radius, and integrated SZ signal. Signal here by Y5R500. As we said before, in order to obtain number counts that are comparable with observations, we need three ingredients, and in particular the selection function. This is a function that relates the true population of clusters present in the sky with the ones that are observed and returned by the MMF algorithm. This can be split in two different functions. On one hand, we have the purity, that is the probability that an observation indeed corresponds to a real cluster. And then we have the completeness, that is instead the probability of a certain cluster in the true population to be observed. I focused on this second one as because the purity of the Planck sample, especially the cosmological one, has been shown to be very high, very close to 100%. So in order to obtain the completeness, there are two different paths that can be taken. On one hand, we can perform a theoretical estimation based on the assumption of Gaussianity of the noise in the SZ effect, and the completeness therefore becomes an error function depending on the integrated SZ signal, on the noise at the cluster scale, and on the cut in signal to noise that we impose on the catalog. This is an example for a given cluster scale as a function of the SZ signal, and we see that at low signal the completeness is equal to 0 because no cluster can be identified, and at high signal is 1 as all of the clusters are identifiable by the method. On the other hand, we can use a simulation-based approach that consists in injecting simulated cluster signals in the sky maps and counting then on how many of these are detected. The completeness then becomes the ratio between the detected and the injected objects. This has also been performed by the Planck collaboration, finding relatively relative agreement between the results and the error function estimates for clusters that are not too small or are not too big, at least. In my work, the goal was to characterize the completeness function using, again, this simulation-based approach, but with a more realistic setup, because in Planck, this was done using spherically symmetric simulated cluster signal. So we want to use more realistic cluster shapes, and a setup where the detection template may differ from the true signal that is in the sky maps. Therefore, we used images of clusters, again from the elasticity TNG hydrodynamical simulation, selected by mass and redshift, from which we took 6 projections per cluster, amounting to a total of about 9,000 images that are shown an example here. In order to compare the results obtained with this method, we also produce a set of spherical images generated from an integrated generalized Navarro-Franken-White profile with the profile from Arnaud et al. In 2010 that shares the same distribution in signal and cluster radius as the simulation images. The methodology that we use, to recap, is to inject these cluster images directly in the real Planck frequency maps, run the MMF algorithm using a spherical cluster template, again with the Arnaud et al. Profile, and then compute the completeness in bins of cluster radius and AZ signal as the ratio of the detected over injected. And these are the results that we find. At first, we can see that in orange, the completeness obtained from the spherical cluster images agrees quite well with the analytical error function estimation. On the other hand, in blue, we see that the completeness obtained from simulation images is overall higher than the other two. This is a rather unexpected result, because we would expect that an incorrect matching between the template and the cluster signal would lead to a decrease in the completeness, not an increase. We believe that the reason for this shift is to be searched in the different average profile of the simulation images with respect to the template. We see in blue that the mean simulation profile is overall steeper with respect to the template shown in orange. This also leads to a bias in the estimated cluster radius, which, as we can see here, for the simulation images is underestimated with respect to the true injected radius. To see if this was indeed the explanation for the completeness shift, we produce another set of spherically symmetric cluster signal using a profile that is as steep as the simulation one. And we obtain a completeness in light blue that is almost the same as the one for the simulation images. Therefore, we conclude that the shape of the cluster profile is the main driver for this shift in the completeness. And as a consequence, we see that the non-sphericity of cluster images that come from the simulation has only a moderate impact on the completeness for Planck. Investigating further the dependence between the shape of the cluster and of the cluster profile and completeness, we tested different sets of spherical images with profiles with different steepness, from steeper to flatter with respect to the template. And we see again that for steeper profile we obtain a higher completeness, while for flatter profile we obtain a lower completeness instead, showing a direct relationship between the two. Also, this is reflected in the bias in the estimated cluster radius that is overestimated for flatter profiles and underestimated for steeper profiles. Then we wanted to test the impact of the change in the completeness on the cosmological analysis with the Planck sample. And therefore, we redid the cosmological analysis, changing only the completeness function. And we obtained that from using higher completeness, that is steeper cluster profile, we obtain lower values of omega m and sigma 8 compared to the standard error function, while with a flatter profile we obtain lower completeness and higher values of the cosmological parameters. This shift in parameters is in the same direction as the degeneracy as the hydrostatic derived from the hydrostatic bias, with higher values of 1 minus b tending to lower values of omega m and sigma 8. Therefore, these two aspects we believe that should be accounted for together in future analysis. So, in summary, the completeness function we saw of MMF in Planck depends on the choice of the template, because if the real cluster profile is different than the template, this can lead to a shift in the completeness. And we saw that the shape has only a moderate impact on the completeness. Then we saw that the shift in the completeness is degenerate with the cosmological parameters for the Planck analysis. To conclude my presentation, as we said in the beginning, galaxy clusters are powerful cosmological probes. But in order to compare the observations with the predictions, we need both an accurate and comprehensive cluster model. In order to improve the cluster model and reduce the possible biases on cosmology, we have two paths we can take. On one hand, we can improve the understanding of galaxy clusters and their properties in order to improve the reliability of the model. And on the other hand, we can assess the impact of the simplifying assumptions on the cosmological analysis to see if they are justified. For these two paths, on the one hand, I studied clusters beyond spherical symmetry, showing that the distribution of matter inside clusters is related to the dynamical state and accretion history, while in cluster outskirts to connected filaments. And I also showed that gaseous filaments can be detected in observations of cluster outskirts with statistical methods. And going forward, further, we can think to apply these statistical methods to detect filaments in larger observations, with larger samples from observations. On the other hand, tested the impact of the cluster model on the completeness of clusters in Planck, and I show that the completeness depends on the detection template. And the shape of the real cluster profile is the main driver of and the shift that can also be important. And this can have an impact on the constraints that we extract from the cluster analysis. Going further, one can think to include uncertainties in the completeness function in the cosmological analysis to try to alleviate the possible biases due to an incorrect completeness, and also test the impact of non-sphericity of clusters for higher resolution observations than the Planck data. And with this, I conclude my presentation, and I thank you all for listening.
Thank you very much, Stefano, for being perfectly on time. So I will leave the floor to, well, if people want, maybe we will leave
Yes.
You missed the important part. They won't get the cake session. So I will give the floor to Professor Margot Lebetrice. If you want to ask questions, please feel free to ask.
Thank you very much. I'm happy to be the first to discuss and to present the questions with the same time, we am the first to congratulate you for the excellent work you have done with it. Unfortunately, you explored a lot of topics that are really interesting to me, and so it is the reason why I filled the 7 or 8 pages of the report with suggestions, comments, questions, everything. All the topics that you touched are really interesting. A question a bit scattered. I have only 1 hour, no? I have my question a bit scattered along your presentation, but I would like to start from the last topic. And so the mainly, did you play with the template that has been used in the match multi-frequency filter adopted for the Planck detection? The template has been derived in average on a limited sample, limited ratio range, everything is limited. And so it's interesting that you wanted to explore how some differences in the template that could be the steepness or the steeper profile and pressure profile or the morphology of the cluster will have an impact on the completeness. And you have shown that the completeness increases, so is higher when at least the profile are steeper.
Yes.
And so what is your idea about the impact of this effect? Because you can say that the average profile in the Planck cluster is biased towards steeper profiles.
Can you just repeat the last part?
Last part is you're showing that the completeness is higher
Yes.
for cluster with the profile, pressure profile steeper than the template.
Yes, yes.
And so you have the more cluster detected with these steeper profiles.
Yes, yes.
And these could have an impact on the final pressure profile in the Planck cluster sample.
I think yes, to an extent. Yeah, obviously it depends also which sample you take, because yeah, what is the threshold in signal to noise, for example, and that one decides to take. But yeah, what we show is indeed that clusters with steeper profiles are more probably detected, and these could have an impact on the profile. It's obviously a bit of a loop, because you have to assume a template in the beginning before knowing the true profile of clusters, and so therefore there might be an impact.
Related to the same topic regarding the completeness, you were showing that the morphology of the cluster, what you were calling the shape, the two-range ellipsoidal shape or spherical shape, the morphology has not any impact on the change of the completeness function. But can be it is a result because you are exploring all the clusters and you are not selecting only the nearby cluster where Planck has some resolution. Otherwise, Planck had a quartz resolution for the faraway cluster.
Yes.
So if you take all together,
this is definitely a good point, because I mean, what we tested was that the completeness is shown at many different cluster shapes, and we see that there is indeed an increase of the impact of the non-sphericity of clusters going to larger shapes. The problem with the limitation that we had with our sample, simulated sample, is that we took it, we say, face value from the simulation using the mass and the redshift, so we could not probe the very high radii that are detected in Planck. Therefore, for the very large clusters, I cannot give you a precise number, but indeed there is a trend, let's say, of more impact of the morphology of clusters going to larger cluster radii, and surely with with observations with high resolutions, that this could be also an aspect that might have a larger impact than what we showed here.
And still related is you defined the bad and the good clusters in terms of morphology using the beta 2, that is the multipolar ratio between the quadrupole in zero order. But there is a zoo of other morphological indicators that can be applied. So should be interesting to check another one because probably beta 2 is a simple one, let me say.
Yes, yeah. It's I use that also because was a method that I used in other studies, so that it was easy to apply it to this data set as well. But already, like, I think that we can see the fact that we can already see a certain even small impact is a hint that the morphology has a role to play in the detection. And I think using another probe for the non-sphericity can be an additional test, but I think that nonetheless this is good enough to show this.
Did you check that the beta 2 you discriminated the good and the bad cluster applying beta 2 on not smoothed maps?
Yes.
And so in the primordial maps that you injected in the Planck without cluster map.
Yes.
And you check if you apply again beta 2 on the smoothed with Planck beam maps, there was any difference in the population? I mean, they're everywhere. All the maps go towards the relaxed, the spherical one.
Sure. Yes.
So then it was impossible to find an impact of the morphology.
Yes. There is surely an impact of the beam that smooths and symmetrizes all the clusters. The fact why we chose to compute the beta 2 on the native maps was to see the intrinsic property of as intrinsic as possible property of the cluster, and how that impacts let's say independently on a priori the whole detection process that includes the smoothing of the instrument.
I would also go back to part two, the beginning, when you were studying the correlation between connectivity and cluster matter distribution, whatever, and you were estimating in this case you were exactly this point. I mean,
yes,
you are checking the correlation between beta, defining that way that is all together.
Yes.
And the connectivity defined in that way. It is the connectivity defined as the number of filaments passing through a sphere of radius 1.5 R².
Yes.
Which kind of filament? The gas or the galaxies?
The galaxy filaments,
Okay.
yes, which are also extracted from the whole simulation box.
I mean, you know that the connectivity is a physical quantity with a lot of paddings. There is for sure the components of the filaments, because you have different connectivity for gas, dark matter, and galaxies. Is another paddings is the projection 2D or 3D. The connectivity is different. We were shown in the 2744. The connectivity 2D is only 3, 3D is 5.
Yeah, precisely.
And then the connectivity also on the filament finder. We are using TX, there are other filament finders.
Yes.
And so this is the connectivity related to beta. And in this case, you are comparing the connectivity estimated at that aperture with other, probably the next slide, other theoretical indicator of the dynamic state, like the relaxation parameter, that is estimated in another aperture. inside the R200, if I
Yes.
remember well. And so when you're comparing connectivity at that aperture with a dynamic estimator at another aperture, could have an impact on the correlation. Because you know that the dynamic state of a cluster is radial dependent. A different over density cluster in the core should be relaxed, and the increasing the over density is going towards the standard object.
Yes, yes. No, what maybe I wasn't precise enough is that these are not the same beta. So these are the beta computed in this outer aperture, while these are the same beta but in the inner aperture. So those are not directly comparable because, as you said, it's a different. There's a difference, and asymmetry of the matter is obviously very different at different apertures. So these parameters are indeed concerning the inside of clusters and are compared with the asymmetry of in clusters of the matter inside R200.
The last one, for me, the one is related to the next step. I mean, the application of this statistical approach on the single specific cluster like 82744. But this is really interesting because you have a, let me call it in a naive way, combo, because you are applying a T-Rex and the multipolar decomposition. And you find all everything, the filaments around this cluster. And I was a bit worried if you, before to do this application on a real cluster, may play a little with the simulation. Because in Illustris or TNGOs, whatever simulation, you should find an object similar, not necessarily similar, where you can find, because you have all the information, filaments, you can generate mock images in X-ray, and in optical, again, you can play to check if the variables that are also in T-Rex that you have to tune are tuned correctly for that specific case.
Yes and no. Surely, yeah, it can be done, and it's a valuable exercise to check with mock X-ray from simulations. But what we found is that the parameters of T-Rex, although they needed to be adapted to the X-ray, say, domain, which was not what they were designed for.
Must be the wrong answer.
So the change of domain needed a change in the parameter values. But what we see is that in the X-ray data, changing the parameters of T-Rex, even by a large amount, didn't impact substantially the results of the filament detection. Therefore, yeah, it could have been done. It can still be done, and it's certainly interesting to try and see what are more specifically the impact of certain choices on the analysis. What we wanted to do here was to have a more direct case study on an object that has already a detection, let's say, of the X-ray emission from filaments, and to see if how we can compare with that.
And the last one is that because you apply T-Rex, making a trick on the map or X-ray map, just to generate what you call the heat map, and all the pixel are one, outside the sun circle. At the end of the day, you have detecting the skeleton of the filaments. But did you investigate something about the temperature, the density, what is the filaments of gases, wind, or whatever?
I didn't do it directly. This was done in the work of Dominic Kerter and collaborators, where they.
Its own filament.
Yes, obviously, yes.
Yeah.
Yeah, no, I didn't.
Just to check if they are substructure, so they are not really filaments.
No, but the fact that we have a good spatial overlap with the ellipses from a character also, yeah,
But just to understand, there is still hot gas or is still wind, and so there's still.
it's mostly wind.
Okay,
I yeah, don't have, didn't redo the analysis
Okay.
myself, but the overlap with the results of the character shows that.
When you are detecting the filaments, you should test it and explore the physics of them.
Yes, this is certainly an avenue for future study.
Thank you. Thank you very much.
Thanks, Stefano, for the very nice presentation and the thesis, which I really appreciated the reading everything. As Marco as well, your thesis touched so many different aspects which I all find interesting. So I do have a lot of curiosity. I'll try to limit myself and just the most urgent one, then we'll do it offline. So going in the other direction, since we're here from the beginning to the end.
Sure.
Maybe you mentioned that, but but looking at this plot, I was I was intrigued by the fact that the distance between the dark matter and the hot gas profiles of theta remains constant essentially for every, according to every criteria here, which is which is defined as the sum of the first moments here.
Yes.
So that makes sense. The hot gas is more spherical.
Yes.
Do you know exactly, which multiple contributes more to the difference between the gas and the dark matter one?
I don't know exactly, but I know that in all the distributions, in general, the order of 2 is the most important on average. So I expect that to be the main cause of the difference.
So that will contribute. The most of the difference between the gas and dark matter.
I think yes. I would expect, as you said, in general, the gas to be more spherical, and therefore all of the multiples to be lower somehow,
Right.
and therefore being the second one the most important. I think
That's
that's
the most power.
Yeah.
Then back to Abell 2744.
Yes.
So I know you have the statistics on the spectroscopic sample is not doesn't allow you to slice the data through in very different ways, but perhaps one could expect that looking at filaments, essentially you might find different populations of galaxy population of properties of the galaxy population. Are there any chance to see whether this is you can find
Well, not with these sample, yeah, because the only information that was in this catalog was the position and the magnitude, basically, and the redshift. But I think that we got more
perhaps maybe if you just use the passive galaxies, you might increase the signal to noise of the filamentary structure.
It's possible, and it's there's related work it's been done on Shapley that also shows dependence on the galaxy population.
Back to Abell 2744. Now that you know where the filaments are, is there any chance to see weak lensing signal associated with them?
I imagine yes. Yes, I think in Eclipse work they also tried that and saw a certain amount of weak lensing signal associated with these structures. So yeah, I think having somewhat more sometimes more refined idea of where the filament might be can improve also that kind of analysis. But yeah, I think there is a hint at least for structure in lensing around those structures.
And on the comparison between was it trick also by the filament on the line of sight essentially? Would you expect that to be observable at some, in some other wavelength or some other observation?
Well, one thing that is surely interesting is that there is comparing these results with the analysis, for example, of Oversetal that first analyzed these galaxy data. There is a very good agreement within the velocity also of these structures and their position in front or in the back. So yeah, I think that is also in this study I took a bit larger sample. Therefore, I expect to have more of these filamentary structures with respect to their data sets.
And in particular, so you first apply corrections based on fingers of God, but then you're seeing filaments on the line of sight. Could that, in a sense, could that impact the corrections that you have applied at the beginning as well, or could it modify the actual true distribution?
I don't. I think if anything, like the correction should, like impact in the sense that it would make the filament less visible. So the fact that we still see it is a very good indication that there is something there. In the method that we applied, takes computes run the friend of friend algorithm on the galaxy data to find the structure, like the cluster itself that gets corrected. So there could be an impact of that in that sense, but if anything, it would just
boost the signal.
Yeah, exactly.
Then maybe back on the cosmological, if I have back on the cosmological side. So so you show essentially how the posterior changes, by adopting different completeness function.
Yes.
I guess there's no way to, from the statistical perspective, to say which one is a better fit to the data, right?
That's how we all want to know that.
No, I wouldn't.
Completely degenerate with the parameters.
Yeah, I know. I wouldn't go as far as claiming that one direction is.
But the fact that the simulation, for example, the simulation profile wants something steeper in a sense. Then you said that yourself it can be counterbalanced by the hydrostatic bias. I don't know. Have you ever tried to see what happens if you're using the simulation completeness and the mask and the scaling relation from the simulation itself to see?
Yeah. That's for sure. No, I haven't tried that directly, but it's definitely something that should be done in a more let's say complete analysis. The example I showed was mostly to show an extreme case, let's say, where shape of the cluster profile, the real profile is different than anything else.
Right.
Basically.
But on that point, I mean, yeah, you're putting the cluster in the Planck mass, but cluster will be actually connected to filaments, right? And we are not, I mean, obviously you don't know where to put that in a,
Yes.
in the, to be consistent. So do you think that might impact in a sense the result? Or?
I'm not sure if Planck has enough resolution to be impacted by any of the outskirts of clusters. So I believe that yeah, for these analyses shouldn't matter that much. But yeah, that could be potentially an issue in different observation.
Can I ask the very last question? So even if it's not included in the presentation, it's on it's on the thesis.
Yeah.
So I was very interested in reading also your chapter on the generative approach.
Yes.
With the students, we are doing something similar with different techniques, and I was really happy to see some of the difficulties that we are finding in your results. That is a common, even if the methods are different. One thing that one question that I had is that like the loss of information that you have on small scales, the fact that you are not able to recover the complete distribution of small scale features. Is that like consistent with a smoothing of the image with the kernel, or is just that you're missing the only the very small scales, but the overall this for example the profile looks like the simulated full simulated profile.
Yeah. It's well, I haven't directly tested the profile shape, but I expect them to be relatively similar in that respect. What I think is happening here is that the model scales are at retrieving the small scales because it's somehow like in the loss descent is driven towards more like average generation that gives a comparable result in terms of loss value with respect to a more precise definition. Probably it's a matter of computing minima and we couldn't find the right combination of parameters to reach the right convergence to get the results.
Then it's a matter also of what's the application that you might be doing now or not.
Yes.
Okay, thank you very much for the
Professor Thank you. And as I am third person to ask questions, it means that a lot of things have already been told. Like my first sentence, that thank you for very interesting presentation and for very interesting thesis. And also some of my questions are already asked. But okay, let's start. In the first part, when you analyze the groups and clusters, you use mass limit 5 times 10 to 13 power solar mass.
Yes.
Why did you choose exactly this thing?
Well, it was to be consistent with the previous work from which we used some of the analysis, in particular the properties, the physical properties.
But then why this limit was used in together?
With it's the more physical answer is of course that in the paper we also investigated the difference between groups and clusters, and therefore the lower mass threshold was also to include galaxy groups to see how the mass dependence of going from groups to cluster has an impact on the rest of the analysis. So I didn't include it in the.
You include everything, it's clear. But in your presentation in the beginning, you told that galaxy clusters are the largest objects to collapse in the universe. But since you mentioned one study in your answer during your answers, I still ask, what do you think about which are the largest objects in the cosmic wave which are collapsing now or may collapse in the future?
Yeah,
Are they galaxy clusters or something?
No, of course, yeah, there are also what are called superclusters that that are obviously collapsing and
No, not exactly. I mean, not the whole, typically not the whole supercluster.
okay, yeah. To be honest, I'm no expert of superclusters. I know they exist. I don't precisely know all their properties and how. I know that their definition is somehow not so easy to define.
Yes, I agree with that.
Yeah.
Thank you. And well, now I have a question about this part where you analyze completeness function. And it's related to cosmological parameters like sigma 8. And there is this famous tension in cosmological parameters. And what is your opinion about this tension? Will it stay? Will it fade away with new data, or will it be stronger? And what is your favorite parameter?
Well, I might say I maybe have a bit of a bias, having worked mostly on clusters. I know someone here might disagree.
Can you leave us? Feel free. But you're not. Just
Yeah.
tomorrow.
No, of course, I don't have an answer for to that, but part of my work was precisely to try and see if some of the assumptions that are made in the analysis with clusters can relieve or exacerbate the tension. And indeed, it's what we show with the completeness, that a different shape of the profile might go in both directions, basically, to higher values closer to CMB or to lower ones. So there is still room for solving the tension without new physics, I think. But,
well, here has already a lot of questions about connectivity. So it seems very interesting topics to everybody. But I ask just to start with, why did you use exactly T-Rex filament finder? And did you try also others, or what is the preference of this finder? And could you expect that results will be different if you use another filament finder?
On the question of why T-Rex, is that it being designed to work on a discrete data sets directly from the position of the galaxies, for example, can be used in simulations or observations alike, which is not the case for all filament finders. I didn't test with others. This is also because we had the availability of T-Rex in the group and the expertise to use it also. So that's part of the reason why we chose that.
But then again about the connectivity of Abell 2744. How high is the connectivity of this cluster in comparison with connectivities of other observed clusters. I mean, there are very few detections, but still you can.
Yeah,
So-
yeah. It's rather, let's say, may vary a lot because for example, observations of comma suggest connectivity more like towards 3, or connectivity of other clusters that are in a more overdense environment have higher connectivity. So there's also a dependence on the environment, obviously. If we consider connectivity of the 5 for 82744, I think it goes a bit on the lower medium range compared to other observations. But there is a question of environment that impacts that as well.
And also there is huge variety.
Yes.
And it's related to some structures and structure culture and everything.
Yes. That's right.
When you characterize clusters,
Mhm.
you use several radii, like virial radius R200 and others. But that is now very popular to determine splashback radius. Have you tried that too? Or have you maybe you saw in your results that maybe you can derive some other characteristic radius of the cluster? And this last question is related to that in chapter 7, your thesis. Some figures, it seems that beta parameter seems to change at certain radius, the cluster. Was like 0.75 also. Could it be some characteristic radius of the cluster?
So I haven't looked in so much in details about what could be a characteristic radius on the splashback radius. We have an expert in the room, and in a study led by Teolugu. They found that it can, like, it's not as maybe not as universal as or clear cut, let's say, usable in all cases, because it might vary depending on the projection effects, and it's it has been argued that it's might not be as like universal as previously thought.
And there has been already a lot of questions. I just asked two more, and one is that you covered so different topics in your thesis. What is your favorite among them, and maybe what would you like to develop further?
Mhm.
And another question is related, and this is, if you are asked to summarize your thesis, the most important thing in one sentence or in a few sentences, what would you say?
I'm notoriously very bad at choosing a favorite. I like very much both the work I did on A20 matter distribution that led to the filament detection in outskirts. That would be very interesting to develop, I think. And on the other hand, the completeness one measures more like the impact of the model on the cosmology, which is also, I think, particularly interesting to test further and to dive a bit deeper into the implications that it might have on the full pipeline. It's a bit more than 2 sentences, but hope it's okay.
Thank you.
Thank you. But I have also a few questions before I give the possibility for the directors to speak. So actually, just going back on the last point, I have a question because you mentioned the profile, the model profile, etc. But aren't you, in some sense, saying that instead of a flux limit, one should look at a surface brightness limit? Because of, in fact, the asymmetry is not really playing a role. The completeness is affected by surface brightness, no? Because the shape will affect, in some sense, how much light you have per unit area. In some sense.
Yeah. I don't know if it's
Because I know that people who study blind catalogs made out of X-ray images, they found that the key parameter is surface brightness, not flux limit. That could mean that the part of the tension that people see is because they don't take into account well enough, maybe that, I don't know. I don't know if it, as you say, if it's not.
might be.
Okay.
Might be. Yeah. There's also I'm thinking about the fact that the bias in the detected radius of the cluster that is also dependent on the on the shape of the profile, and I'm not sure how that impacts in turn the selection.
But by the way, when you were asked the question between what's the largest collapsing structure and but in my opinion, what you're talking about is not the largest collapsing structure. There is another word that I would have used, which I don't think you used.
Large bound structures.
Yeah,
I
realized structure.
Yes.
That's the difference with the photocluster.
Yeah.
Because if you say the largest collapsing structure, then you may not. That's a lot. Yes.
Yeah, probably.
Because the key point is that it's realized.
Yeah, that was what I wanted to say.
Yeah.
I don't remember now what I said.
Because you didn't mention it at all during the really that they have to be varialized.
I think it was in the very beginning.
Oh, okay.
Yeah, I went through it a bit quickly. I concede. But yeah, when I talked about this, it was in the very beginning.
Which is obvious, of course. Actually, I have a question related. I have just two more questions. One is when you looked at the beta versus accretion rate.
Yes.
Yeah, for example, here. I was wondering, so for me, the accretion rate can, I don't know if it's a tracer of the intrinsic mass of the structure or a tracer of the fact that if I take 10 clusters of the same mass in different environments, they will have different accretion and therefore they have a different sphericity or whatever. So here I'm confused because I don't know what you're measuring, because let's say maybe if you're 10 times massive, you accrete 10 times more. It has nothing to do with the accretion, the actual environment. So I would have thought that you would normalize that per unit mass, or like to make sure you have. Did you check that it's not dominantly due to the mass of the structure, or if it's an environment effect or not?
Yeah, I see what you mean, and yeah, definitely there's
because maybe a proxy for the mass.
Yeah.
Okay.
I don't have it on the top of my mind at the moment. If it was
So here it's mixing all masses, I guess, from 5 to the 13 to whatever, 10 to the 15.
can't.
So maybe the low masses are on the left, and I don't know.
I think that's yeah.
Okay.
Try to remember, but
Maybe you can check that later.
yeah. I definitely.
A last question I have is when you have your filaments traced by the galaxies,
Yes.
You have spectroscopic redshift for them.
Yes.
Did you check if you had global dynamical signature of the movement of the galaxies? Like you could have taken like beams of galaxies and see if if they are blue or redshifted on the right and left side, for example, to see, you have two filaments like that. Maybe one is blue shifted, the other one redshifted, or whatever.
Yeah. Well, from the distribution, you can see that the filaments identified from the central panel show that these are rather perpendicular to the line of sight, and yeah, they connect at different places in the one more in the front and one more towards the back of the glass.
Well, that's the 3D spatial distribution, but I
Okay.
was wondering whether you saw dynamics, like galaxies.
Yeah.
You know,
In you mean like with okay? I think that was also included in the work of Owens et al. That showed not as far as we are probing, but showed that there were some sort of say dynamical similarity between galaxies in those directions.
you mean like they are moving towards the structure or something?
No, it was more like that they have a coherent.
You mean the orientation of the galaxies, the shape of the galaxies?
No. There was they tested if the galaxies are somehow like taken from the same velocity dispersion, like the velocity distribution. Yeah, and then they found that the galaxies in these areas are part of the same population. That's,
I see.
no, but I don't think it was checked
Okay.
if they have a coherent motion.
Yeah, okay.
But no, I don't think that was checked.
Okay.
At least in the because I don't think that was checked. We didn't do it.
Okay. Thank you.
Can I just, the coherent velocity is the Z direction in this axis.
Yeah. Somehow, yes.
But here you have a static view of the,
There is a
because you have some in the line of sight where you could see there. You have the central velocity of the structure, and you could see if let's say galaxies, some filaments that go towards or not. Okay.
It's like you have statistically very large sample, or you can see it in simulations. But if you have only a few solid galaxies, then it's very difficult.
Yes, perfect.
And I think that so.
Yeah. Thank you. So.
No, okay, this is okay, so you can start. So please go ahead. Okay. I would like to thank you for these several years of working with you. And it's super nice to see all this path since we first met for your masters. You were even shyer than today. It's not believable, but you were really shy. I like very much the work that we've been doing together, the discussions, your curiosity, you're going really into the details of what you do. It's always super emotioning to see the evolution of our young colleagues, and I think that we did really a good job. The topics were very various, very wide. Some were very complicated and didn't completely went through as the generative work. But I think that in each moment you really managed to, to do the things until the end, and to be able to rebondir, I don't know how to say this in English, to start from what you were and jump to another topic and very courageously, very enthusiastically. So thank you for all of this, for the nice discussions, and I hope you all the best for the future.
My turn. So thanks for the presentation. I really liked reading your manuscript. I think it was really nicely written, and it was nice to read as a supervisor. Easy to read, so it's good. Thank you for that. Thank you also for choosing me as a co-supervisor in your thesis and work with me and others during these 3 years. I enjoyed it. Yeah, maybe just come back on some part you didn't present. I think your PhD is a nice example of how science and in research is going. We had a really nice idea at the beginning of the thesis, really nice plans, and wanted to do many things. Obviously, you have to focus on one, so we started with something. It didn't well so good as we thought. We didn't manage to go to the end of the story. But again, as Nabila was saying, you managed to rebondir. Now I have the same word in my mind. Start over. You worked. You did your best for that. You managed. You succeeded. And here we are with you presenting all the work. So congratulations. Again, hope the best for everything else. Thank you for your effort, your work, and working with us together in the team. Thank you.
Okay, so then the jury will meet and discuss. Where do we go? Do we stay here or do we go?
You can go in a small room there.
Okay.
We'll have to leave the
On est bon?
Ouais, c'est bon. So Stefano, the jury discussed a long time for a simple reason is that they had so many things to say about so many things you did. And for me, it took time also to take notes of the, of the report because you've been working on a wide variety of wavelength, a wide variety of techniques, a wide variety of scientific questions, addressing problems which we think are both innovative and bringing important insights on important aspects of astrophysics, in particular cosmology, but also the nature and evolution of galaxy clusters themselves as probes of the evolution of the universe, but also as objects by themselves, filaments. We've been impressed by the fact that you had the courage to start new techniques, to compare different techniques, which is not common. Usually one could use one and it would have been enough, in fact, for your PhD. You can take 50% out, you have a PhD in some sense. But we were impressed by the fact that you could check the consistency and even modify tools that were existing. For example, T-Rex for galaxies, you modified it so that you could study it in the X-rays, etc. So, which is, and you were able to converge, because that means that you have a very good ability also in managing software and managing data, theoretical aspects as well as observational aspects. I won't go into all the details that I will write in the report, but globally, we've been very impressed by the amount of work that you've done. And we encourage you, I mean, it's your decision, of course, but to continue in this direction because you have proven that you're an independent researcher able to succeed in what in the task of being an astronomer and being able to take the right decision. So, as a conclusion, the jury unanimously decided to congratulate you for your PhD defense and to give you the PhD, knowing that there is no more the cum laude in the university. So, but we are all very happy to greet you for your PhD.
Thank you so much.
You have something to read, I think.
So, in the presence of my peers, with the completion of my doctorate in astronomy and astrophysics, in my quest for knowledge, I have carried out demanding research, demonstrated intellectual rigor, ethical reflection, and respect for the principle of research integrity. As I pursue my professional career, whatever my chosen field, I pledge to the greatest of my ability to continue to maintain integrity in my relationship to knowledge, in my methods, and in my results. Yeah, I just wanted to say a few words of thanks. First of all, to the jury, thank you so much for being here and for listening to my work and judging it not for a PhD, and I'm very grateful. The most enormous thanks to my tutor, Pantalon. Really, thank you so much for taking me as a little bit lost master student and helping me grow throughout these 3 years. It's been really a pleasure to work with you and to work here in the group and really thank you so much for on the scientific and on the human side. I think it's finished.
You have 50 minutes.
So also very special thanks to all my colleagues and friends at IES. Really, has been a wonderful time here, and thank you for making all the time I spent
very special and full of nice things inside and outside the lab and the working hours. So thank you all so much. Yeah. Really, really, really thank you. Grazie, grazie Stefano, anche a Francesca, a tutti, tutta la famiglia che segue da casa, a tutti gli amici qua e da casa. Ho appena cominciato a leggere i messaggi, ma risponderò con calma. No, grazie davvero a tutti quanti. Ein besonderer Dank, die ganze Sophia. Ohne dich, mein Leben wäre viel leerer an Freude und Abenteuer. And yeah, danke, danke. And yeah, I think that's I used up all my languages. And now. Merci. Merci. Now I feel there is no doubt.
Look forward to
it.